and welcome back to AGT STEM. Today we're going to be watching a video on Nihonium. So without further ado, let's hop to it. It's a long video, so hopefully you stay in there. Let's get to it.
Element 113 is the only one that I've discussed with an ambassador. In fact, it's the only one I've discussed with two ambassadors because I've discussed it with both the old and the new Japanese ambassador to London. And the reason why I was discussing it is because element 113 is the first element to be definitely synthesized in Japan. And so it is a huge excitement in the country. I was in Tokyo in February this year, 2016, and I met a representative of Riken, the lab where these elements were synthesized, and they gave me a press release about the element. The really exciting thing from their point of view is that they get to choose the name of this element. Now you have to understand that making these so-called super heavy elements is not a quick process. It's not like boiling things up in a test tube and finding a new element. It takes years and years and years. And over the history of the search for elements, the last 200 years, there have been hundreds of claims by people believing that they have discovered new elements. So now the process is extremely rigorous, and now they've got to the final stage and the name has been chosen. The name they chose was Nihonium, which is a Latinized version of the Japanese name for Japan, nihon. I'm sure I've pronounced that incorrectly. The experiments that led to this discovery began a long time ago, more than 12 years ago. And like all elements of this part of the periodic table, they're made by taking a heavy element, in this case bismuth, atomic number 83, and a light element, this case zinc, accelerating the zinc to a huge speed, and the nuclei fuse together to make an element of 113. What you have to realize is that you take billions and billions and perhaps trillions of zinc atoms to get one atom of element 113. Apparently, the Japanese lab observed 3 atoms over a period of 9 years. So this is not something that you do quickly on a Friday afternoon and publish the next day. A huge amount of verification is needed to make sure that what you see is genuine. And the way that you detect these elements is that once they're formed, they shoot out of the back of the bismuth target onto a detector, and then they decay radioactively into a chain of different elements. And this chain of elements tells you which element you formed, because soon you get to part of the periodic table where you know how the elements decay. What is amazing, though, is that people can also tell a little bit about the chemistry of these elements. You can only do a limited amount of chemistry when you have one atom at a time, but what they can do is to bounce the element, the atom, when it's ejected, off some sort of surface, say gold or Teflon, and see if there is any difference between the way they stick. You can tell quite a bit about the element just from the sticking. And in fact, the measurements have been made, and element 113 does stick to gold quite strongly. This part of the periodic table is really unusual because just by chance, the way the atomic numbers add up, the number of the element, 113, is the same as the group it's in, or at least the 13 is. It's in group 13, the same element as boron. And if you go down, element 113, nihonium, is just below thallium. And we know quite a lot about the chemistry of thallium, particularly it's very poisonous. Now you can't tell whether nihonium will be poisonous because you only have one atom. Even if you could get one atom inside somebody, it would not poison them chemically though its radioactive decay could cause damage. One of the things that's really interesting about thallium is that it has 3 electrons in its outer shell, and in its chemistry it can lose either one of these to make thallium plus salts, or it can lose all 3. And I suspect that in the chemistry of element 113, the +1 state would be even more prominent than in the chemistry of thallium. Because if you go up the periodic table in the same group to aluminium, you don't get aluminium plus at all. Nihonium is in the same group, so it has 3 outer electrons in just the same way as thallium, assuming that the electrons are arranged in the same configuration. Because when you get to these large atoms, their energy levels of the different shells are very close together, so it would be possible, at least in theory, for the configuration to be different. But people assume that it will be 3 electrons arranged in the same way as in boron, but much larger shells. The difficulty is that as the atoms get bigger, if you imagine the electron like a particle, they have to go round and round in the shell, and the speeds they're going round approach the speed of light, and therefore their mass changes and you get so-called relativistic effects. We made a video about this on the properties of mercury, which is a much lighter element than element 113. So people will have to do quite a lot of calculations, and in the end, unfortunately, these will just be theory because it will be very difficult to verify them. Now, the important question that people always ask is, what on earth is the point of making elements like this? And the answer is that it gives us a much better understanding of how the protons and the neutrons in a nucleus bind together. And it's only when you look at the extremes, when they are binding together relatively weakly, that you can test whether your theories are any good. So, although it's an enormously expensive experiment, the results are really very useful.
Professor, do we not already know enough about how protons and neutrons work? I mean, we can make atom bombs and nuclear energy. We understand the everyday elements very well. Why do we need to know more? Have we not sort of got our head around it enough?
The radium nucleus threw off an alpha particle consisting of 2 protons and 2 neutrons.
The importance of these experiments is that there have been predictions that when you get very heavy elements, the so-called super heavy elements, they may become more stable than one might expect. In general, what has been found as people have gone up to heavier and heavier nuclei, they've become less and less stable. But now there is some indication that these very heavy elements are more stable than one might expect. That doesn't mean they're very stable. They may only last a small fraction of a second, but that's longer than people might have expected just by extrapolating the lifetimes of the other ones. I think it's a great honour to anybody, to any country, and I think it is a very nice example of collaboration between different countries, because although it was discovered in Japan, its existence was verified and justified by experiments in Germany and Russia. So it's a very good example of international collaboration. I find the name slightly difficult to pronounce, but it's a lot better than Nihonium, which I find almost impossible to pronounce. This is the press release, and on the back is a photo of the leader of the team, Professor Morita, with presumably the periodic table showing his element. But the thing I really like is the quotation at the end. It says, "For Morita, then part of the coming year will be devoted to thinking of and proposing a formal name." They've now done that. But he's looking forward to the next step in his research. "We plan now to look to the uncharted territory of element 119 and beyond, aiming to examine the chemical properties of the elements in the 7th and 8th row of the periodic table, and someday to discover the island of stability." So, all being well, there'll be lots more periodic videos on the subject. Oh, I'm wearing a Japanese happy, which was given to me in Tokyo by a great fan, Nagayasu Nawa, And you can see, unfortunately, element 113 comes here in my armpit. It's a really nice periodic table, and it's even better on the back. Walk along and see where the ions go.
Thank you so much for watching, and we'll see you next time. Stay smart. Bye!